All right. Nice to see you all. It's been a while. Hope you guys been doing well. So as Zunor has previewed, we got a lot of stuff to cover. It's okay if we can't finish it today. I know you guys also have a deadline tomorrow. There's a lot of code snippets as well. We're not going to go line by line. We're just going to highlight the key parts that actually implements the concept that we're going to try to learn today. So, yes. So we saw from the previous lecture, the concurrency is one of the key feature operating systems, but by enabling multiple threads to actually operate, sometimes they might interfere with each other, right? By trying to process certain important parts, right? So we call that the critical section, and we want to make sure it's executed in a single atomic instruction. In other words, only one thread uses it at one time. So a very basic example of critical section could be like, update of a shared variable, which we saw from the last lecture. So one way to basically ensure that is to create locks around it, right? So here we define a lock, and then in between this critical section, we have a lock and unlock. All right, so that's the basic idea. Sounds quite simple, but as in many systems, the devil's in the details. So we define a lock variable, and it basically represents state of the lock, right? It's either available, meaning it's free, no thread has it, so probably I can just lock it. Or if it's already acquired some other thread, and only one thread is using it, then you don't get it. Now, so the semantic here is when we call the lock, we try to get the lock. If no other thread has a lock, then we acquire the lock and we become the owner of the lock, right? And then we enter the critical section. And while we're doing this, all other threads are prevented from entering the critical section while this thread holds the lock, right? So this provides some minimal amount of control over scheduling to programmers. So let's look into a pthread lock. So this is mutex, which is a POSIX library that used for the lock. So mutex is basically representing mutual exclusion, because that's what we're aiming for. So here, pthread, mutex, lock, you have an initializer. Now this one is actually a wrapper because we just added to exit when it fails, right? So again, in between, so basically in between the lock and unlock is a critical section. Now we could use different locks to protect different variables, right? Or we can choose to just use one lock for all variables. Obviously that'll be more slower, but perhaps easier to manage. But if you have multiple locks, different locks, then you increase the concurrency. So let's try to build a lock, right? So we want to build a lock. First of all, because since we're engineers, we want to be efficient, right? Low cost. And as with many, many concepts we have already learned, we're going to need some help from both the hardware and the operating system. Now, how do we evaluate locks? Meaning, what's the metric of locks? So let's talk about some metrics. So what do you guys use? Let's say you guys have project mates, right? At the beginning of the class, what's the metric you used when finding your project mates? There could be many metrics, right? Anybody? Friendship? Okay, friendship. Anything else? Competence? Huh? Coding skills, yeah, competence, coding skills. Anything else? Personality, okay. Work ethic? Load in terms of other courses, right? Many, many metrics. But what's the most important? And there's no right answer. I'm just asking your opinion. What is the most important metric when you evaluate your project mates? Oh, okay. So you just ask them? That's a good one. Yeah. Okay. What about love interest? Boyfriend, girlfriends, whatever. What are some of the metrics? No metrics? Yeah. Are you guys all desperate? Come on. What are you looking for? Hang on, maybe you can help us out. Responsibility, like, what do you mean? Like when you send her her or him, I don't judge, send her a message, you reply back, or what do you mean by so you want, like, what's the deadline? How how quickly do you have to hear back? Yeah. All right. So you don't care anything else. Her character, looks, but the responsiveness. Okay, it's an interesting one. Zunor, how about you? Since you talked about metric as well, what are some important metric for your love interest? But it could happen anytime. Did these things happen like without notice? You need to be proactive, man. You're very reactive. Okay. Okay. Subin, the TA, what about you? Personality? Anything else? Humor. Okay. So far, I haven't heard about looks or wealth, competence, vision of life. Nothing. Education, like level or which school? All kinds of ways. Okay, very high bar. Can I ask you, do you currently have a girlfriend? Okay, and she passed all the metrics? Wow. Well, I would love to meet her sometime, yes. But yes, so basically there are many metrics. Now, in this case, the lock, I think the first one is absolute must, right? Mutual exclusion, right? Because that's what locks are for. You want to make sure only one thread access it at one time, right? It's about correctness, right? Now, the other two, at least to me, it'll be great to have, but if you don't, as long as you provide correctness, this is something we can build on, right? So fairness. Does each thread contending for the lock get a fair shot at acquiring it once it is freed? Because in the extreme case, some thread might get into starvation. They never have a chance, right? So it's not fair. The third is performance. By implementing a lock, does it take more time? How much more time? Of course, this goes into the efficiency issues, important, but I think first one is non-negotiable. So we're going to go through a bunch of schemes that build locks. And as we go further, I think we will improve because we're going to start with the simple ones. And some of them might not even satisfy mutual exclusion. So as we saw from the race condition, the previous lecture, is that because of bad timing sometimes, bad timing of interrupts, these race conditions actually happen, right? So perhaps what we could do is when we're going into critical section, I will disable interrupt, right? I don't want like untimely interrupts. I'm just going to disable it, right? So this was one of the earliest solution. And obviously this is invented a long time ago. We're thinking about single processor systems. So basically void lock is disable interrupts. Unlock is, back to enabling interrupts. Very simple. However, this requires way too much trust in applications, right? An application could say, oh, I'm just going to get a lock. And you don't unlock it. You just, entire time, you just have exclusive access to the CPU and nobody else has it, right? Malicious. So again, if you look at the history of all the algorithms in computer science, initially, they're all very trusting, right? You would think everybody would be nice until, you get hit by the security bugs. Obviously, this will not work on multiprocessors. So we need to do a little bit better. So the first attempt is using a flag, right? It's just a bit. So lock is basically an integer, which is a flag. So what we do here, first initialize it. So value of 0 is lock is available, right? Nobody has the lock. If the value is 1, it is already locked. So initialize it to 0. So the function lock here, basically, while mutex flag is 1. So you test it. If it's already locked, then you do nothing, or we call it spin wait. You're just going to wait until it becomes free. Once you get out of the while loop by knowing that when you test, the flag is 0, then you set it, right? And then you enter the critical section. When you're done, you unlock it by setting the flag back to 0. Very simple case. However, this one has problems. First of all, there's a correctness issue. So let's assume initially the value of flag was 0, okay? Now thread 1 first called lock, right? So if you go back to the previous code here, lock, now while flag is 1, sorry. So you are in here while flag is 1, so you are spin waiting. And as you are about to go into the next statement, you're going to interrupt because you're out of the lock. Now, thread 2 here calls a lock. You go through the while loop, and then it sets the flag 1. Then you got interrupted. You go back to thread 1, and now both threads are entering critical section. So that was the first problem, which is a correctness issue. Second problem is, efficiency and performance. Basically, spin waiting. That's really wasting time, right? So we're going to need some help by the hardware, and we're going to next go into something called test and set, which is also known as atomic exchange. So basically what it does is first when you get the pointer, you put it in the old. So you fetch old value at the pointer. Now, the new value goes into pointer and then you return old, right? So what it does is first you return or test the old value pointed to by the pointer. And we'll see the use of this function in the next slide. At the same time, you update or set the set value to new, and this sequence of operations performed atomically. So basically here, you have a lock, you initialize it. So your functional lock would now look like while test and set, the logs flag 1. So this is, so here, pointer, logs flag is now going to old, and that is being returned. So the current value of flag would be returned, and then you also set that to 1. Now, if the current flag is 1, then you spin wait again, right? Otherwise, you have the lock. Right, and of course, the unlock should be straightforward. Now here, one note here. If this has to work on a single processor, it needs a preemptive scheduler, meaning there needs to be a timer-based preemption. Otherwise, it could be just spinning the whole time. So let's look into test and set and all other what we call spin locks, right? Basically, you wait until your lock's available. Until then, you're just doing nothing. Basically, waiting. The next cycle, you check again. So this, in terms of correctness, yes, it works because it only allows a single thread to enter the critical section. Is it fair? No, because spin locks don't provide any guarantees. There's no guarantee every thread would have opportunity, because a thread spinning may spin forever, right? In terms of performance, let's say if you have a single CPU, and again, you're going to have to spin quite a bit. Not good. Now, however, if the number of threads roughly equals the number of CPUs, not bad. All right. So it works, but it looks like we still have room for improvement. So next we go into something called compare and swap. Here, test whether the value at the address pointer is equal to expected. Here, pointer. Now, if so, then you update the memory location pointed by the pointer with the new value. In any case, whether the result of comparison is true or not, you still return the actual value at that memory location. So here, compare and swap, you have a pointer. The actual is basically whatever value in this location. Then you compare whatever is here with expected. If the same, the new value goes in to the pointer. So if you look at void lock while compare and swap here, if the value of the flag is 0, right, expected, then this is 1, then you set to 1, and you basically spin. So instead of test, so these are a little bit different, but still same logic. The next one is called load linked and store conditional. So load linked, basically, basically you return the pointer, but now the interesting part is here, store conditional. So here, you have a pointer and a value. Now, if no one has updated the pointer since the load link to this address, then the value goes into pointer, and this is success. Otherwise, 0. So what this does is, now this only succeeds if no intervening store to the address has taken place. So it hasn't changed, it hasn't been updated. So you return 1 and update the value. If it's success, otherwise it's not updated, 0 is returned. So you can use that in the log here. So while true, while low linked. So basically, if the flag is 1, then you spin. Now let's say this becomes 0, so now you're in the if, right? Now if store conditional load, so basically flag is 1 equals 1, meaning if set it to 1 was a success, then we're good. Otherwise, you go back to the while and try it all over again. So that's another mechanism for the lock. Now, the down below here, basically the author of the textbook teaches at Wisconsin, and he said one of the students actually learned this, and he said, he or she said, oh, you can actually do this in this even shorter number of lines. And yeah, so he actually included this in the text. So you can actually be more precise or concise using load, link, and store conditional. Now there's yet another one, which is called fetch and add. Again, very simple concept here. You increment a value while returning the old value at a particular address. Okay, so when you have a pointer, it's in the old and return old, and the pointer is old plus 1. So we're going to use something called ticket locks based on the fetch and add. Now, ticket locks, this is a concept we actually use in real life. When you guys go to a bank, what do? First thing you do, go to a bank, take the ticket out. It has a number. And it has a board saying, well, I got number, I don't know, 95. It says, we're serving number 76. And, you know, oh, fuck, I need to wait like 19 turns, whatever, right? This is exactly that. You wait. Right? So you get a ticket. So basically here, now first of all, yeah, so lock now has a ticket and a turn. So fetch and add. If my turn is basically whatever shows in the ticket, and if the turn is not the same, then you spin, meaning you wait. Right? So if you think about the bank or even those hot restaurants where you have to take a ticket, you wait, but you never felt this is unfair, right? Whoever comes first, when it's empty, you get served. So it provides fairness. However, all these spinning, right? It's not very efficient. So they work, but it wastes an entire time slice doing nothing but checking a value. You check a value, it's not what I want, oh, I wait. So that's the entire cycle. Not very smart. So how can we develop a lock that doesn't necessarily waste time spinning on the CPU? So we're going to need some help from the OS as well as hardware. Now, again, let's start simple. One way is, okay, I have to spin, then what I'm going to do is I'm going to give up the CPU. The previous mechanisms, you still held the CPU. You're just waiting, but you held it. How about we actually give it up? Yield, right? So OS would move the caller from the running state into the ready state. However, the cost of a context switch could be quite substantial, right? Because that also incurs some overhead. And the starvation problem still exists. So here, basically, you test and set. If the value is 1, you yield. Another way is to actually use queues, right? So you keep track of which threads are waiting to acquire the lock. So here, when you go into the queue, or let's say we're in the bank, if I'm number 95 and they're serving 76, perhaps I should just sleep, right? So you park, push a calling thread to sleep. So when you park, you just know you're You're the one who's going to park. So you do it. Sometimes when you unpark, you have to actually specify the thread ID, right? So you wake a particular thread. So now the lock has a flag, guard, and a queue. So guard is basically to protect the queue, basically spin around the flag. That's the only thing here. So here, basically, when you're locking, so this part is when you have the lock acquired. Otherwise, you add yourself to the queue. Now you need to call get thread ID here, and you park. When you're unlocking, right? Basically, when you're unlocking, if the queue is already empty, then you just let go of the lock, or else you unpark by you unpark the one that's queue removed, right? You hold lock for the next thread. So one way was to ill, simply ill. The other is just go to sleep. Now, in this sleep wake case, sometimes, again, due to very bad timing, somebody might sleep forever, and we don't want that, right? So let's say thread A is releasing the lock just before the call to the park by thread B. Then thread B potentially could sleep forever. So one way to prevent this, and Solaris does this, is to introduce something called set park. So set park means I'm not parking, but I'm about to park. So by calling this routine, a thread can indicate it's about to park. If it happens to be interrupted, and another thread calls on park before the park is actually called, then the subsequent park returns immediately. So when you try to park, it says, no, you can't. Right? Because otherwise, you're going to sleep forever. Right. So the rest of this part 1, I'm going to skip. Just says different OS provides different supports for locking mechanism. Yes. And then one last part was, there's, sleeping, and there's also, spinning. And as typical, when there's two different schemes, somebody tries to merge it, and that's the two-phase locks. So what two-phase lock does, in the first phase, the lock basically spins. If it acquires a lock, great. If it doesn't, then it goes into second phase, which is to sleep. So initially, you don't go sleep immediately. You kind of spin it. Then you feel, I'm not getting my chance. I'll just go to sleep. So that's a two-phase lock. So that's the lock. Spent 30 minutes.